Hello, welcome to my next tutorial on how to analyze your laboratory data. This is how to analyze the protein gel picture that was sent to you earlier this week. So here's a picture of the gel that I sent you. What you need to do is make this into a suitable figure for your report, and you also have to do some measuring so that you can get an accurate molecular weight on the protein that you purified from the gel filtration column. So let's label the lanes first. Just use numbers 1, 2, 3, 4. And then you should identify what's in each lane in your figure legend that will be below your figure. So we'll just call this figure X, since I don't know what figure it'll actually be in your laboratory report. But you would give your figure a title, something like SDS polyacrylamide gel and our gel was a 4 to 20% gel, so put that in your figure legend. Electrophoresis of the acid phosphatase purification. So that's a suitable title. Then you need to identify what the lanes are. So just say something like lanes 1 is molecular weight standards. 2, maybe just put a parenthesis, 2 is sephadex fraction. 3 would be the dialyzed protein. And then 4 is the crude extract. So use the numbers that you put on the lanes. Don't write counting over from the left. The first one is blah, blah, blah. Put the lane numbers in there and refer to the samples by number. Okay, so the next thing you have to do is figure out where the molecular weights are on this picture. The molecular weight values are in your handout from the lab on page 3. And they're listed as kilodaltons, I believe. So we'll just do that for the gel as well. So KDA, the first one is 250,000, then 150, 100, 75, and so on. The last one is 10. So fill those in. You can either print out the picture and write the numbers in by hand with a pen. You can import the picture into your Word document and then put a text box here, a vertical text box, and write them in. Any way you can think of to get them in there is fine, but they need to be on your picture somehow. The next thing you're going to do is measure how far each of these proteins travels and make a plot. And the way we do that is by calculating something called an RM. That stands for relative mobility, and that's equal to distance band travels over distance of tracking dye. The tracking dye is the blue dye that's in the sample buffer. If you had made the samples and run the gel, you would have added a blue dye, and that's a tracking dye. So that's how we determine the length of the gel, essentially. So we don't actually have the tracking dye on this picture. It would be down here, but this picture was taken after the gel was destained and the tracking dye disappears. So for our denominator, we're going to use the distance of the gel, the whole gel. So you measure from the top of the gel, and on the top of the gel you use the bottom of the well as your measurement. So we're going to measure from here, and we're going to measure all the way down to the bottom of the picture instead of the tracking dye. And in this case I'm getting 25.4, let's say. 25.4, so RM will equal 25.4. It's almost 25.5, but we'll call it 25.4. It doesn't matter what the units are because you'll have the same unit on the top and the bottom and they'll cancel. So now for our first band, which is the 250 kilodalton one, we'll measure that. And I'll count that as about 4.7 roughly. And if we do the division there, we will get 0.7. We get about 1.185. So that would be our RM for the 250 kilodalton molecular weight. So do that for all of these molecular weights except for not the bottom one. I would skip the 10, just do the 15 and higher. This band is so wide and blurry, it'll be hard to get an accurate measurement on it. So just do the other ones. And you want to measure to the middle of the bands. So if they're a little bit wide, pick the middle of the dark part. Don't do the top or the bottom of the band, do the middle. So do those, calculate all those RMs, and then you will plot them versus, or you'll plot the weights versus the RM on a plot like this. So you'll have log of molecular weight on the y-axis and RM on the x. And if you do it correctly, you'll get a negative slope. It's going to be like that. Then you can get your linear trend line for your standard curve. And then you need to compare that equation to the distances your actual experimental proteins migrate. This is also covered in your textbook on page 223. So if you want to look in the textbook, it's page 223. So going back to our gel, what you have to do in terms of calculating is you have to determine the molecular weights of the bands in your sephadex fraction or the most purified fraction on the gel, and that would be lane 2. So you have 2 bands there that you have to determine the molecular weight of. So measure how far they travel, so it'll be 2 measurements, and divide them by the value of the entire lane. So go from the top of the bottom of the well down to the bottom of the picture for your distance of the tracking die, and then divide that into how far each of these bands migrate. When you get those 2 RM values, you will put them into this plot, and they will go in for X because RM is on the X, and you will be solving for Y this time. Keep in mind that your Y equals log of molecular weight, similar to the gel filtration column. So you will have to get to the molecular weight, you will have to take 10 to the X of Y, and that will equal your molecular weight when you do the calculation. So you will get 2 molecular weights because there's 2 bands, and then you will compare those 2 numbers to the value you got for molecular weight with the gel filtration column, and one of them should be closer than the other one. So you can decide based on that that's your acid phosphatase. But for the other band, you should look online and use the internet to find out if there's other acid phosphatases that have a different molecular weight. Because if there are, you could assume you've isolated 2 different acid phosphatases. If there aren't any other ones that match your molecular weight, you can assume it's a contaminant. So that's something you should look up to put in your discussion. And I think that's all you need to do with the plot. So I hope that was helpful. I just remembered one other thing you should do when you look at this plot for your report is it's not a calculation or something you have to come up with a number for, but you can use this gel to figure out if your purification was successful based on the number of bands in each lane. So in this case, we'd be comparing the crude extract to the sephadex fraction. The dialyzed protein should be similar to the crude because we really haven't taken very many proteins away between these two steps. But from the dialyzed protein to the gel filtration column, we were hoping to purify some of the protein away. And based on that Bradford data from the gel column, we should have purified some protein away. So you compare the amount of bands in these two columns to this column. And if there are less in this column than these two columns, you can say that the gel filtration column helped to purify it because a lot of the protein's gone. So that's the last thing you can use this gel for. Okay, now I'm done.